Good evening, everyone. My name is Swaraj Bari, and today I'll explain my project about self-supervised learning on SwinIR transformer. So basically, SwinIR transformer is a architecture which has been suggested in a research paper. This is used for image restoration, but till now, what researchers have used is supervised learning for image restoration till now. As you can see, SwinIR performs very well, but in this approach that I'm going to tell you, which is basically implemented by another research paper. I'll link the research paper in the description. So in this we are trying to train our transformer based on a self-supervised learning approach. Now one might think that self-supervised learning and unsupervised learning are both the same thing, but they are actually not, which I'll explain to you in a few seconds as we go forward. So I'll first talk about why this approach is important. Why do we need um, self-supervised learning? So as we know that in supervised learning, we can see in this research paper as well that we need so to obtain a high quality image, we first feed a low quality image, and it will transform it to a high quality image. But to train that model, we would actually need examples in the training set. We will need both high quality image and a low quality image now, and that would be our supervised learning, and that would be how we will optimize this with by using a shore loss. I think they use a shore loss here, but definitely when we use supervised learning, we will need both kind of an images, high resolution and a low resolution. Now the problem in real world arises basically mostly in medical field, that we maybe have an image of some internal organ, but that is sort of a fuzzy or a blurred image. Now we cannot obtain exactly the high resolution image of that exact situation of that exact person. It would be impossible. I mean, suppose if a doctor is doing an operation and he cut a patient and he grabbed a photo, and then the doctor says to the patient that the photo that we took is sort of blurry, let us cut you again. So I mean, he won't let him do that. So in such scenarios where obtaining a reference image to train the model is very next to impossible, or we can say very costly or unethical, we use self-supervised learning, and this is the paper that I'll link. So first of all, I'll show you. We'll first deploy the model that I had made, and then I'll explain you. So we are in the WSL virtual environment. This is Ubuntu environment. Let's first make the deployment, right? Sorry. Yeah, so it will deploy for now, and we will be having deployed Streamlit app in a few seconds, I think. We'll probably have it here. So yeah, we have it. So yeah, so this is a demo application. Definitely will yeah, I'll hide it for now. So I'll first show you some sample blurred images that we have, right? So see, these are the kind of blurred images. These are just random images that I took from the internet and sort of added some more blurriness to them with a separate fault function. Now our model is basically a linear inverse function that I'll explain later on. So as you can see, these are the blurred images that we will ask a model to unblur. So first of all, let us try and input one image here. Since this is a local deployment, it will be quite slow because I don't have a GPU on board. So yeah, it is running now, and Till it's running, I'll explain you the architecture. I'm very sorry for this hand-drawn picture because um, I'll just explain the architecture. So, since in this approach we don't have a fully high resolution reference image, we just take our blurry image, right? Then we pass it to our neural network or our transformer. Our transformer is basically a SwinIR transformer that is this, and I'll explain this to you in a moment. Just bear with me. So this is a neural network, and then it will give us a slightly unblurred image. Basically, the first initial values will be random. What we will do is we will downscale it to again this resolution of our blurry image, and after we have this image, we will add some noise to it again. We will make it blurry again as well, and then we will pass it to the same neural network that we have, and again we obtain a slightly blurred image. Now you might be asking, why do we unblur an image and then blur it again, then again unblur it? This is all to find the loss. So when we have our blurry image first and we unblur it, later on we calculate a loss. This is the Shor loss, and you can also call it a reconstruction loss, right? And we save it for now, and then we downscale it again, and again you can see we have a similar sort of situation when we have a blurry image and we unblur it. Now what we do, this is also unblurred image and this is also an unblurred image. Between these two images we calculate another loss, which is an equivariant loss. Right now we add this Shor loss and equivariant loss, and we get our proposed loss. When we optimize on this loss using the Adam optimizer, and we keep the beta in between 0.9 to 0.99, we get pretty good results. I'll show you. And this neural network or the transformer network is basically the SwinIR network. Let me explain that to you in a very short way as well. So basically we have an image here, low resolution. We pass it to a convolution layer of 3 by 3. Now the transformer layer consists of many blocks of residual swin layer transformer blocks. Now the number of these blocks depends on the depth that we give. So here it is 6, and in each of these blocks we have another swin transformer layer. Now this, and again the number of layer, it depends on the depth that we give. So the swin transformer layer is like this. We first layer normalize our input, then we apply a multi-head self-attention, we concatenate it again, then we apply a normalizing layer, and then we apply a multi-layer perceptron here. These are all transformer terms. I hope you understand it. And we use this whole block in a single residual block, and we use the number of blocks depending on the depth that we give. And after that we apply a convolution layer, and we also concatenate the first input through the last. And then again, as you can see, the residual blocks are again here, and then we concatenate the first to last. So each and every block is having the concatenation, right? Now after this we have the image reconstruction module. This is basically a subpixel convolutional layer if we are opting for a super resolution image, or if we are opting for just a simple de-blurring algorithm, we just use a simple convolution layer and we get a good resolution image, right? So this is the basic architecture. Let's see if it has, it has done the unblurring. So this was the normal image, and this is the processed to the trained image. Now this depends sometimes on the weights and the training of the model. If you do it on a Google Collaborator, you will probably get results in a faster time and even better results, if I would say so. Let us try for a different image as well with this one. Again, it will take time, so I'll just cut it off, uh, and I'll show you. See, the algorithm is running and probably requested the transformer API as well. So yeah, it is running fine, and I'll see you in the next project.